So this is continuing the series of short lectures on counting. We're working towards getting 4 formulas for counting different kinds of collections of objects. And I'm not going to actually get to the formulas in this short talk. What I'm going to do right now is establish some vocabulary so that you can recognize what are the 4 kinds of things that we will be counting when we get the formulas. So what we're doing is we're counting the number of possible ways that you could make collections of objects by choosing members from a set of possibilities. So you get a big bag of possibilities, and you're going to maybe a big bag of candies, different kinds of candies, and you're going to pull out some of them and make a little collection, a sample from the bag. Okay. Well, there are 4 types of ways that you might be doing this, depending on, does it matter what order they come out of the bag in? Like if you're giving out candy for trick or treat at Halloween, and you've got 3 kids lined up, and you're going to pull out 3 candies, and you give the first one to the first kid, and the second one to the second kid, and the third one to the third kid. See, the order that you pull them out in might matter to the kids. They consider it 2 different things. You know, if it's Hershey bar and Reese's cup, and then Milky Way, that's a different thing, a different permutation, a different order than if they came out in a different arrangement. So one thing that matters, you know, is the question, when we make these collections, these like subsets, you know, you got a big set of candy in the bag, and then you're pulling out a subset. If the order matters or not is one decision. It'll tell us which formula to use to say how many ways it could have happened. Okay. Then the other factor is whether repetition is allowed or not. Maybe I'm selecting names from a hat. No, I've got 3,000 counties in the United States, and I want to choose 36 counties as a sample to go and study them. Well, there are 2 ways I could do that. I could put all the names on popsicle sticks in a big box and shake it up and pull them out one by one. So I get 36 different counties. Or after I pull out one of these popsicle sticks, I could write down the name and throw that stick back in the box, shake it up again, and that would allow for a small possibility that I might get the same one twice. So the question is, am I going to allow repetition, getting the same one twice, or not? So those are the 2 decisions. Does order matter? And is repetition allowed? And that's why we have 4 different types of collection. When I say collection, I mean we've pulled out of the big bag, we've got a little collection of members, and it might be ordered or orderless, and it might allow repetition or not. And that gives us 4 ways, 4 different situations where we might want to count the possibilities. And we'll have 4 different formulas one for each of those situations. I'm not going to show you the formulas today. I'm just going to talk about how to distinguish the four types in a story, okay, and do a little comparison between them. So now here's a table where I've broken it down into ordered versus orderless, repetition versus no repetition. I get four kinds of things. And I want to start with the combinations because that's the one that's probably most familiar to you. This allows no repetition. You cannot choose the same item twice, but order does not matter. The set whose members are 1, 3, and 2 is the same set as the one whose members are 1, 2, and 3. It's the same combination of three numbers. Okay. So an example of a word problem of this type would be, how many ways can I choose 3 different neckties if I have 5 of them in a drawer? Just how many different sets of 3 might I produce by reaching in the drawer and pulling them out? Okay, so those are combinations. And I'm not going to give you a formula yet. We'll work all that out in great detail. I can give you a symbol for this, though. So the way you pronounce this is in, choose, R. Like if the question was, given a set of size 3, how many subsets of size 2 are there? That'd be 3, choose 2. Now, I'm going to show you how to count that, but without a formula, because it's such small numbers, I can just list the possibilities. So I'm only doing this just so you'll know what I'm talking about when we do come around to getting the formulas. So here's a set of size 3. Its members are A, B, and C. How many combinations of 2 letters can I make from that set? Well, there's AB, the set whose members are A and B. There's the set whose members are A and C. And there's the set whose members are B and C. So 3, choose 2 equals 3 because there were 3 ways to do it. Now when the numbers get bigger, it gets really hard to make the list. So that's why we'll get a formula later. I want to compare this with permutations. Okay. Permutations are like combinations in the sense that repetition is not allowed. So if the question was, how many permutations of size R can you make from a set of size N? I'll give you the symbol for that. It's NPR, like National Public Radio. Okay, so this time it's like my ties in the drawer that I just told you about. So this time it's not just how many ways could I choose 3 ties, different neckties out of my drawer if I got 5. Now the question is, how can I choose 3 different neckties and give them to my 3 different uncles? So here are 3 of my uncles, Bob, Howard, and Jim. Here's my 5 solid colored neckties. There's lots of ways I can pick 3 ties. And if I do it this way, brown, blue, red, that's not the same as if I did red, blue, brown. See what I mean? It's not the same. It's a different way of handing out the ties. Okay. So combinations is just how many ways can I choose the 3 ties. Permutations is how many ways can I choose them and then put them into different orders. How many different ordered sets can I come out with? So in a notation on this, if I write ABC, that's not the same as ACB. Now, for the combinations, I used this brace symbol, the squiggly parenthesis. For the permutations, I use the curved parenthesis. And you're already used to this from algebra. You know, like in algebra, you could graph points. And the point 1, 3 is not the same as the point 3, 1. See, we use the parentheses for ordered collections, and we use the squiggly brace for unordered collections. Now, in algebra, it was okay to have 1, 1, but that's not a permutation. You can't have the repetition with permutations. So they're ordered with no repetition. Now let me do like I did with the combinations and with the real small numbers. Show how I can make the permutations. So I'll start with a set of size 3 again. And now I want to list the permutations, like I listed the combinations up here. But this time, order matters. So instead of just having the combination whose members are A and B, I have AB, and I list the combination BA separately. It counts different. My uncles care which tie they got. Okay. So it's like Bob gets A and Jim gets B, right? Okay. So then you've got AC, and you've got CA, and you've got BC, and you got CB. So 3P2 equals 6. there are more permutations than combinations. Okay. Well, now what if we care about order, like the permutations, AB is different from BA, care about the order. This time, though, we're going to allow repetition. We're going to make ordered collections allowing repetition. And these are called words. So an example would be how many 3-letter words are possible in a 26-letter alphabet. You see, order matters. B-O-G, bog, is not the same as G-O-B, gob. 2 different words because the order, same letters, different order. Okay. But with words, you can allow repetition. T-O-O, two, is a word. And so that's what makes the words different from the permutations. Now we're allowing repetition. So examples of that, how many 3-letter words are possible in a 26-letter alphabet? See, you can think of a tree diagram. There are 26 choices for the first letter. And then once you got your first letter, there's still 26 choices for the second letter because repetition's allowed. Yeah. Okay. And then you go from there. So like just to get up to where you've chosen the first 2 letters, there's 26 times 26 possibilities. And by the time you get to 3 letters, it's 26 to the 3rd power. Another way to think, like just for the first 2 choices, you had A, B, C out to Z, and then you've got A, B, C down to Z, you know, and each box here, this would be A, B. Like A, B, or C, D over here in one of these boxes. C, the first letter from here, D from here. So there's 26 times 26 different ways to get your first 2 letters, and then for each one of those, there's 26 ways to pick the 3rd letter. Okay, so how many 2-digit decimal numbers are there? So yeah, it's 10 times 10. There's 100 different numbers. You got your 00, your 01, your 02, all the way out to I'm sorry. All the way out to 99. 0 through 99. So there's 100 different two-digit numbers. Makes sense. Now those are, for counting purposes, those are words. How many two-letter words are possible in a 10-letter alphabet? Now the last one, and actually when we're making the formulas, this will be the hardest one, is the multisets. You allow repetition and you don't care about the order. So I'm thinking here about like making a banana split. I got 5 flavors of ice cream to choose from. I'm going to put 3 scoops. I can have 3 flavors in my banana split. The thing is, I can repeat if I want to. I could have 3 scoops of chocolate. Okay. So repetition is okay. I just don't care about the order. If it's chocolate, vanilla, chocolate, I got the same thing as if it was chocolate, chocolate, vanilla. You know. Well, I mean, I'm not going to care what order it's put on the plate. I don't know. If I was very much younger, if I was a kid, I might have had an aesthetic preference there, but okay. So, and you notice here I was picking 3 flavors with 5 to choose from, but I could just as well pick 5 flavors from among only 3 choices. I mean, I can pick more than I have because of the repetition being allowed. Okay. So those are multisets. It's got a symbol too. So NMR example, I have I have 3 kinds of tool. I've got pliers, wrenches, and hammers. And how many ways can I choose 5 types to carry outside to the car? Okay, so how could I take, if I've only got 3 kinds, how could I possibly choose 5 kinds? Well, with repetition, so so a multi-set like that is okay. It's 2 pliers and 2 wrenches and 1 hammer. And I don't care about the order that I put it in. I might make it my habit. I really should have listed that. I can list them in alphabetical order all the time. Since the order doesn't matter, if I want to alphabetize just for convenience, I can rearrange those any way that's convenient. It's the same thing as hammer, plier, plier, wrench, wrench. Whichever way I write it, it's the same multiset. And I might just make it my habit to always write these in alphabetical order, especially if I'm going to list a bunch of these, and I want to make sure I don't list the same thing twice. If I've got them organized that way, I can avoid listing the same multiset twice. But whichever way I wrote it, it would be the same one. Okay. So that's now. In the other examples, I made the lists. With this one, it's a little bit hard. I'm going to do something like that, but I'm going to do it in a later video. So when I get around to working out the formulas for all four of these, you'll see more illustration with the multisets. But I'm going to leave it for now. In this table below here, I'll distribute this thing as like a PDF file or something like this to the class, but I've got some Excel functions that can do these things for you. But I don't even want to talk about the Excel functions yet until I've worked out the formulas by hand so you understand them, you understand the reasoning. It's really the reasoning process that I'm after, for how we get these formulas and then how we use them. And so I'll show you the Excel functions eventually, but for now, let's leave that be. We'll call it a day for this video, and we'll come back with some later videos to work out the formulas. So I'll see you in the later videos. Thanks. Bye.